I think. Came up with Ohm's law. And the cool thing is ohm sounds like omega, and then they use the symbol omega for ohms. This, I'm going to jump back to the notes from a few days ago. Voltage, current, resistance. I never really gave you good definitions before, but I want to do that now. But I want to go to, maybe this is it. Yeah. So this is what these were the notes from the other class. This was the analogy. This is like the lazy river. Malachi, you weren't here for this, right? Okay, so I need to get you a copy of this. This is the lazy river. And here's
I was there for that.
Oh, you were there for that? So here's the pump, and the pump is producing this pressure that's pushing the water through, but there's this thin spot right here that's slowing the water down. It's preventing it from flowing very well. And here we've got an electric circuit where instead of a pump, we've got a battery. And instead of water pressure, we've got what's called voltage, which is sort of like pressure. But it doesn't push water, it pushes electric charge. And the electric charge is called current, just like the water is called current. So this I stands for electric current. Goes through here and it hits this resistor, which could be a light bulb, could be whatever, but that kind of slows down the flow and it goes on and on. All right, so that's, just want to put some formal definitions down. So voltage, I'm going to call this the pressure that pushes charge through a circuit. I'm going to put it in quotation marks because it's not really pressure, but I think it's good to think of it as pressure. Missing a U in my through. And if anybody wants me to scan this and print one out for them, I can do that. If you'd rather just listen and not have to write, I don't mind giving you a printed out copy. Some people find it's helpful to write stuff down. Some people find it just slows them down. They can't pay attention. So whatever. Yeah, so just follow along and I'll scan this and I'll print one out for you later. So in fact, I think I've already got it on I've already got a copy on my website. I can just print it for you. The units for this are volts. And the symbol, this is really easy for voltage. Symbol is, guess what letter? A V. All right. So voltage is the easy one. Current is probably the most confusing one in terms of what the units are and what the symbol is.
Wait,
So
what's a transformer?
Transformer is
Isn't that
there.
like a bunch of power just like in a box?
So if you look at the ones out on out at the road, they a lot of times those are cylinders, and it depends on what kind. But the ones at the road, let me do electric transformer.
Oh, yeah.
House. Let me put it just house. I bet we can find a good picture of one. There we go. There's one. That's kind of typical right there. Open this up and
Yeah, like that.
So this is what's called a step-down transformer. And see where it says, maybe you can't see it, 240 to house, 240 volts. So this wire, this is they're calling it the distribution line. This is where all the voltage is coming from. And it could be 800 volts, 1,000 volts, something like that. That goes into the transformer, and then the transformer steps it down to 240 volts, which goes to your house.
What if the transformer exploded?
They do sometimes.
Yeah, one exploded at 6 1 time.
Yeah. I don't know. I don't know exactly how that works. What's going on in the transformer is kind of complicated, but that's what it does. You can have a step down transformer, or you can have a step up transformer. If you want to increase the voltage of something, you just basically run the transformer in reverse. So voltage is the pressure that pushes the charge through a circuit. Current is the amount of flow in an electric circuit. And this is the one with the confusing units and symbols. So the units, there are two ways to, or maybe even three ways to do it. You can say amperes, that's the full word. Amps, that's what most electricians say. And you can also just use the letter A. So the letter A on an electrical device is the number of amps or amperes, and that's the amount of current. But the symbol, when it's in a mathematical equation or in a diagram, I don't know why it is, but it's a capital I. No idea why. If you find out why current is an I, you let me know. I feel like maybe I've looked it up at some point, but I don't remember. So in my mind, it all starts with voltage. You get some voltage, that creates this pressure. The pressure pushes the current starts to flow. You have more voltage, you're going to get more current. And then there's resistance, which is sort of not exactly the opposite of voltage, but it does the opposite. It slows the flow down instead of speeding it up. So it's anything that resists or slows down the flow through a circuit. Why do I keep forgetting the U on the word through? So sometimes a resistor, the only point of the resistor is just to slow down the flow of the circuit. If you've got a circuit and some electronic device and there's too much current in it, you'll put a resistor in there just to protect the electronics, just so it doesn't get too much current and overload something. Most of the times, resistors are things like light bulbs and power saws and computers, things that are using the electricity but also slowing down the flow. So the units for resistance are ohms, and it's spelled OHMS, and the symbol, well, the units are this. It's not really the symbol for resistance. Does anybody know what this is? That's the Greek omega, right. So omega stands for ohms. That's pretty good. The symbol, though, if it's in a mathematical equation or you draw it in a diagram, it's just going to be a big R. And that makes sense. That R, I see why they use that for resistance. I still don't see why they use the I for current. Now, Ohm's law is just an equation. It's just V equals I R. And hopefully, as we go over the next page or so, you'll see it makes a lot of sense. It should be a sensible kind of thing to you. The V is volts or voltage. So this is the pressure pushing something through a circuit. What's the I? This is a little test, remember? I stands for what? Current. And R, what's R? Resistance. And sometimes we're going to find voltage using this equation, sometimes we're going to find current, sometimes we're going to find resistance. So if you're comfortable with algebraic manipulation, and then you can solve for R or for I or for V, great. If you have trouble with that, or if you just like triangles, you may want to use this triangle method. Has anybody ever heard of the triangle method I'm alluding to here? Have you ever seen this? So it's just a trick to make the math easier if you like it this way. So you take an equation that's something like V equals I times R, or it could be A equals B times C, or whatever. The two things that are multiplied together, you put them down here, and then the other thing goes up there. And the way this works, so let's say, can anybody tell me if your math teacher said, I'd like you to solve this for I want you to isolate I. Give me what I would equal. Can anybody tell me how you would do that? You'd do what? You wouldn't subtract R. Divide by R. So if you divided both sides of the equation by R, then when you divided the right side by R, the R's would cancel out. And over here you get V over R. So the answer is I equals V over R. Now if you have this triangle, you use it, if you want to know I, you cover up the I, and there's the formula, V over R. If you want to solve this for R, cover up the R, and it's V over I. If you want to solve this for V, cover up the V, and you just get I times R. So use the triangle if you want, do it however you want, but you'll need to know Ohm's law and be able to solve for these two things. Here's a little bit of practice. A circuit has a resistance of 5 ohms and 3 amps of current is running through the circuit. What's the voltage? So I'm going to just write the formula again. Does anybody have an answer before I do it? How many volts would it take to make a 5 ohm resistance circuit have 3 amps of flow through it? 15, yeah. So V equals IR. In this case, I, which one of these is I? The 5 or the 3? It's amps. So current is I. Current is also amps, so it's 3 amps. It doesn't really matter the order you do it in. And the resistance, that's the ohms. And why amps times ohms equals volts, we're not going to get into right now. Just know that it does. If you multiply amps times ohms, the units are going to be volts. So this is 15 volts. There's the answer. So that's really the easiest kind of question. If you're finding voltage, you just have to use it in this form. It's just current times resistance. So number 4, how much current runs through a circuit with a voltage of 20 volts and a resistance of 4 ohms? See if you can do that one. And I'll do it in just a second. Looking for current. All right, does anybody have an answer? What's the current, Lex? 5 amps, good. So I'll use the triangle. If I'm looking for current, I cover up the I. You know what? I'll get to that in a second. I'm going to print this out for Mal. So if I cover up the I, it's just V over R. So my formula is I equals V over R. And V is 20 volts. And R is 4 ohms. And if you do 20 divided by 4, it's 5. And the units for current are amps. So try this one now, number 5. And while you're doing that, I'm going to print out a completed copy of this.
Yeah, can I go?
You want one too?
Yeah,
Okay.
also, can you go?
All right. 4? 5?
Okay.
Maybe I should give them for everybody. Sure. Let's see.
I heard of that.
Yeah. Oh, here we go. Ooh, but this backside, I'm going to want you to try, because we need to practice that.
So is Ohm's law
V equals IR. That is the law, yeah. Looks like my camera is taking a while. Taking a little break. My camera is. Hopefully it'll come back to life. Okay. So does anybody have an answer for number 5? What's the what is the resistance? 2 watts. 2. What are the units for resistance? Well, R is the symbol. Yeah, 2 ohms, and it's the symbol. The this it's kind of confusing. The symbol for the unit is the omega, but the symbol for resistance is R. That's weird. And I'll just use the same kind of process here. If I'm looking for R, I just cover up the R, it's V over I. And the voltage is 12 volts. The current is 6 amps. We get 2, but I need to think about what are the units for resistance? It's ohms, 2 ohms. So number 6, I would like people to try this, whether or not you, even if you haven't been taking notes so far, I want you to try some of these. I'll get you started on 6A. And it's once we're done with 6A through D, I'll hand out the copies that I just printed out. But I want everybody to give this a shot. So this says, write Ohm's law in a way that shows what's happening in a circuit when voltage is kept the same but resistance is decreased. So I'm just going to write Ohm's law, V equals IR. Try to make all the letters the same size. That's important here. And the change that's going to happen is I'm going to have the same voltage, so I want to keep my V the same size, and I want to decrease resistance. So I'm going to make a little tiny R there. And really the question is, what's going to happen to I? So think about what these things mean. Voltage is the pressure pushing the current. Visualize a little lazy river of water moving around. I, that's the amount of flow. That's the amount of current that's flowing through this lazy river that's being pushed by this voltage. R is the resistance to the flow. So what's happened here is I've got the same pump making the same pressure, but have I increased or decreased resistance? Decreased. So if I have the same pump with the same pressure and now there's less resistance in here, what's going to happen to the flow? We're going to get the same flow, more flow, or less flow? It's going to be more, right? So I'm going to make my I bigger. So that's what will happen. So this next one, I'll set it up and then you try to figure out what's going to happen. V equals IR. That's Ohm's law. Voltage is kept the same, but current decreases. So that, same V, but now I've got a tiny bit of current. See if you can figure out what happens to R. The order of this, there's a little something weird about the order. It might bother you. But, okay, what kind of an R do I need to draw? Little one, big one, or medium one?
Big one.
I need to draw a big one. And the reason I need to draw a big one, up here, I had the same pressure. I reduced the resistance, and that's going to give me more flow. The way I would think about it here is the flow decreased. I had the same pressure. What must I have done to the resistance? So if you've got the same pressure, but you've got less flow, does that mean you put more clogs in the system or less clogs in the system? Which one would reduce the flow? More clogs. So I realized that must have been an increased resistance that caused this. So see if you can do the next one. I'll just write this part. See if you can figure out what letters should be bigger, what letters should be smaller, how this should work. Current is increasing, resistance is kept constant. Think about what this means, what the current is, what the resistance is, and how that can possibly make any sense. So first, this isn't really giving you any help, but current increases. So what letter is current? I. So I need to make the I bigger. And resistance is kept constant, so I need to keep the R the same size. So what happens over here? It's got to be a big V. That's the only way this can make sense. The only way, so if I picture again, I picture these are hairballs in the pipes. I've got the same number of hairballs in the pipes. I haven't changed that at all. But somehow I've got a lot more current flowing through them. The only way to make more current flow through the same resistance is to provide more pressure, more voltage. All right, and then see if you can do that next one. So on this last one, what happens to voltage? Does it increase, decrease, or stay the same? Stay the same? Let's check. Does it increase or decrease? Increase? Well, let's check. Resistance is going to decrease. Current is kept constant. So I'm going to draw a little tiny R. There's not much resistance. This is like removing all the hairballs that were here. There was a lot of resistance. Now I've got a little resistance. Current is kept the same. So I'm trying to make I made the I a little too big. The I should keep the same size. All right, that's about the same size. So I've got the same flow as before, but I've got less resistance now. So what kind of push or what kind of pressure does that require if I've got less resistance but no more flow than I had? Less, yeah. So if I kept the same voltage, if I just kept the voltage like this and I reduced the resistance, then that would give me a really big current. So in order to keep that current from getting bigger, I've got to reduce this too. So there's a numerical way to think about this as well. If you just think of these, if you assign numbers to these, let's say this is 100, and this is 10, and this is 10. This would be like saying, okay, this is still 100, and now this is 5. So over here we've got 10 times 10 is 100. If this is 5, what's I now? What's 100 divided by 5? 20. So 5 times 20 is 100. So numerically, if this one goes down, this one has to go up. In math, have you ever heard of direct proportions and inverse proportions? These are inversely proportional, which just means if you keep this one the same and this one goes down, the other one goes up. So in this case, if I keep this 100 and I make this 5, then this one's got to be 20. So that one's got to grow. Now it looks like here I haven't kept this one 100. Maybe I made this one 200 and I kept this at the original 10. So this has got to be 20. So I can do 10 times 20 is 200. And now here it looks like, what did I do? Resistance decreased, so I made this 5. And I kept the current the same, 10. 5 times 10 is just 50. So this had to go down. This is normally 100. So you can think of it in terms of numbers, but it's probably the best exercise here to think of it in terms of pressure and flow and resistance, or I think of that as hairballs. All right, let me pass out these to the people who want them. People at home watching the stream are going to be really bored for a while. Luckily, there aren't many of them. What's that? Oh, just if somebody missed today, people would be watching. It's a little frustrating. So there's a little bit more to do on the back, and This is kind of a random connection. It's just I had this space, and we're about to do a lab where you're going to be setting up series circuits and parallel circuits. So it's a good time to introduce it. Draw a circuit with 2 resistors in series, 12-volt battery and 2 3-ohm light bulbs. So draw your battery like this. Make a big electrode and a little electrode. Although a 12-volt battery usually has 2 electrodes the same size. The other class couldn't answer this, but what common device uses a 12-volt battery? Where do you see 12-volt batteries in the world? In a car. Very good. Oh, man. You put them to shame. So on your car battery, these 2 electrodes, they're not different sizes. How do you tell them apart? How do you know? One's red, one's black. Now, do you know this? Which one's positive, the red or the black? What?
The red.
The red is positive. Very good. All these answers correct. So yeah, one of them on your car battery, one's gonna be red, one's black, and the red is we always show charge coming out of the red one. So if this is the red one, there's charge coming out of the wire, and then it's gonna go back to the black or the ground. Yeah.
Does it actually come out of the red?
Technically, electrons go the other way, and technically, it's not like any electron ever goes all the way through this and around. It's more like, imagine you've got a big long line of people, somebody here, somebody here, somebody here, somebody here. The person right here at this end bumps into the next person, that bumps the next person, that bumps the next person, and that bump travels all the way down the line and through the device. So at the other end of the wire, when we get back to here, there's one person kind of bumps out, one person bumps in, but it's not like everybody goes all the way around in the circle.
Okay.
So it's the electrons actually go out this way, and they move super slowly. It would take a really long time for them to ever get around the wire. But what's called the signal of, as soon as you connect this one pushes the next one, that pushes the next one. It's like a wave at a sports event where people stand up and sit down. You know, the people don't go anywhere, but the wave moves around really fast.
Okay.
All right. Good questions. So 2 resistors in series. I'm going to draw light bulbs, and there's a certain way I'm going to draw them just to make sure they fit in my diagram. I'm going to draw, here's the part of the light bulb with the threads, and this is the part that lights up. So here's my light bulb. And I'm going to draw the wire going in here and then coming out the bottom. And then I'll draw another light bulb like this over here. There's the part with the threads. Here's the part that lights up. And the wire, I'm tempted to do it in a different direction this time. I'll do it in this direction. Go in there, and I'll come out here. It doesn't really matter. It completes the circuit either way. And I think in the beginning I was going to have us do something with this, like find the resistance of this whole circuit, but I'm not going to bother with it. But still, I'll write 3 ohms right here and 3 ohms right here. This is just, I don't really know what the resistance of these light bulbs would be, but let's just assume they're 3 ohms. I'm going to grab a light bulb too. Show you over there what I'm talking about. There's probably, for light bulbs that are in your house and in the ceiling here, there's probably a preferred direction, but I don't know what it is. So this is where one wire needs to connect, and then anywhere over here is where the other wire can connect. So you could have electricity come in here, and then, I don't know if you can see it. Let me see if I can even focus on this. Can you see the little tiny filament in there? There's a filament.
Yep.
So the electricity goes in through this metal, goes up the left side of this wire, goes through the filament, and then back down, and then comes out this tip right here. And that filament is a lot stronger than the steel wool that we used, and the inside of the bulb probably doesn't have much oxygen, so that filament doesn't burn up like the steel wool did. It just glows for a while. Although if you put too much voltage and you get too much current in here, it will blow out. So that's why in this lab we're going to try to limit the voltage to 6 volts. So this is what's called series. And I mentioned last class, if you have a serial killer, they kill one person, and then the next person, and then the next person, all in order. So it'd be like this killer's going through the wire, killing this one, killing the next one, and going on back. Or a TV series where you've got one show and then the next, all in order. This next one is called parallel. So I'm going to draw the battery the same way. This will be a 12-volt battery. And I guess I'll draw the light bulbs kind of oriented the same way, but I'm going to draw the wires differently so that instead of the electricity having to flow from one light bulb to the next, it's got a couple of different options. It doesn't have to go through both light bulbs. It can go through either one, or yeah, it can go through either one. It can't go through both. And to make it look parallel, I'm going to draw it a specific way. I'm going to draw that wire going like that. I'm going to draw another wire down here going like this. And these kind of look parallel. This looks parallel to that. But here's the parallel part. There. So in this one, the electricity, some of it's going to go through this bulb, and some of it's going to go through that bulb. And if these bulbs have the same resistance, guess how much of the total, like if this is the big part of the river right here where all the current is, guess how much of the river is going to go through each channel? What's that? Half, yeah. If you put something with a lot more resistance here, then more water is going to go through there. But if they're equal bulbs, we can just say that the amount of current through here is going to be half of it's going to go through here and half of it goes through there. If you look at a series, here's the main river right here. How much of this main river goes through this bulb? All of it. How about this bulb? All of it. Yeah, there's no other way. So all the current has to go through everything. So when we get to the lab in a little while, one thing I want you to assume about current, I want you to assume that we're using the same kind of bulb, so they've got the same resistance. In a series circuit, the current through each bulb is the same as the current coming out of the battery. In a parallel circuit, the current through each bulb is the same, but they sort of add up to the current coming out of the battery. So if you had two of these, each one would have half of this current. If you have three of these, each one would have a third of the current, so on. Guess which one? So Malachi, you need to know this one. Which one of these do we use in houses more often? Series or parallel? Do you know this one yet? The bottom one? Yeah. Do you know why? There are a few reasons. So anybody, Will? Right. So don't do this because then you'll have to draw it again. But if I remove this bulb, and then we've got this wire coming in here, and we've got that wire coming in there, that's fine. So the electricity can't get through here anymore, but it can still go through there. If I remove this bulb, the electricity gets to here, but it can't get to there without the bulb in. So if we used series circuits in a house, that plug that's over there in the wall behind me, that receptacle, we'd have to have something plugged into it and on in order for all the other receptacles to work. As soon as you unplug that, you just open up the whole circuit. So we use this. The other thing is this. If you think about the pressure coming out of the battery, just imagine how much pressure I have here, and then we run into this hairball, and then we run into another hairball, and let me put another one in just for emphasis. I've got another resistor here. So do you think you're going to have as much pressure in this wire after going through all these clogs as you have coming right out of the battery? No. So what that means is, if we had a circuit in the room that was 120 volts and you wanted to run a saw, you could maybe run the saw here. But if you have a saw and also a sander going at the same time and also a hairdryer, with all those resistors, you're not going to get as much voltage. You're not going to get the full 120 volts. But in this kind of situation, you are. It's not like this clog right here is going to prevent more pressure from coming in over there. So you get more voltage with a circuit. You get the advantage of one thing goes out, other things can still stay on. The disadvantage, the only one I can think of, is this is going to use a whole lot more power. It's giving you more pathways for electrons to flow or for charge to flow. You'll use more power this way, but that's okay. Lex?
I think I.
Okay. So the question, which one is more common in household wiring? It's parallel. And there are a lot of reasons, but the main reason is because if we want items on a circuit to continue to, because we want items on a circuit to continue to work when other items on that circuit are removed. And on your paper, I might have written it a little bit differently. All right, that's that. So let me I'll give you the lab. This is something to work on, and you can work on it in groups of 2 or maybe 3. If you have too many people working together, then I need to stop the stream. Too many people working together. Sometimes I leave the streaming for a long time.